In this video, we're going to start talking about some more formulas when it comes to trig functions. So in 7.2, we're going to be talking about sum and difference formulas. So basically what these are used for are if you have the sine, cosine, or tangent of a sum or difference of angles, then we have a way to evaluate that. So this is when we start trying to solve for angles that may not necessarily be on the unit circle, but maybe we can find a combination of angles on the unit circle to figure out what the sine, cosine, and tangent of these angles are, if that makes sense. So as I told you in the previous video, make sure for this chapter that you're keeping track of all of these formulas that we're learning. And my suggestion would be make flashcards. Again, when you're doing homework problems, like if you need a formula for a question, write it at the top of your work before you continue to work the problem, and that'll help you remember them a bit better. But also, as we go through, I will be giving you tips on how to remember them a little bit more easily. So let's start with the sum and difference formulas. So we're going to say that U and V are angles, and we have the following sum and difference formulas. So first, the sine of U plus V is equal to sine of U cosine of V plus cosine of U sine of V. And then number 2, sine of U minus V is equal to sine of U cosine of V minus cosine of U sine of V. All right, so those are our two sine formulas. So our next two are going to be cosine. So third, the cosine of U plus V is equal to cosine of U cosine of V minus sine of U sine of V. And fourth, we're going to have the cosine of a difference. So the cosine of U minus V is equal to cosine of U cosine of V plus sine of U sine of V. And then finally, we're going to have our two tangent formulas. So number 5, we have tangent of U plus V is equal to tangent of U plus tangent of V divided by 1 minus tangent of U times tangent of V. And then finally, we're going to have the tangent of a difference. So tangent of U minus V is equal to tangent of U minus tangent of V all over 1 plus tangent of U times tangent of V. Okay, so this is a lot of formulas, and I warned you about this. In this chapter, we're going to be learning a lot of formulas. But let's just quickly discuss how we can more easily remember these. So in my opinion, I think the most important two for you to know would be number 1. This is going to highlight. Come on. Okay, I guess it's not going to highlight. So we're going to switch the pen color to red, and I'm going to star the ones that are more important. Okay, so if we look at number 1 and number 3, in my opinion, those are the two most important ones to remember, and let me explain why. So if you notice, equations 1 and 2 look very, very similar, except you have a plus in one of them and a minus in the other. And the same with equations 3 and 4. You have a minus in the first one, a plus in the second one. So if you can remember equations 1 and 3, for 2 and 4, you just have to remember to flip the sign. Okay. Now 5 and 6, these can be useful, but we also know that tangent is equal to sine over cosine. So one thing you can do is you can never use the tangent formulas at all. And anytime you need to solve a problem with tangent, you can just use sine of theta over cosine of theta. So what this means is that you could expand the top of the fraction using the formula number 1 or 2, and then you could expand the bottom using formula 3 or 4, and then you could divide them. So it might be slightly more work, but it's less formulas to remember, and that always helps me. The less I have to remember, the better. Okay, so that's my spill about sum and difference formulas, so let's actually jump into some examples. So I want to start with these true and false questions that we have below our formula box. So the first one, we have sine of 30 plus 60 is equal to sine of 30 plus sine of 60. So the reason I made these true or false questions is because usually people get really confused with this. Because normally when you see something outside of a parentheses, your first instinct is just to go, oh look, I can distribute across the parentheses. Well, sine, cosine, and tangent are different in that we cannot do that. So that would be bad. Okay, so sine of 30 plus 60 is not equal to sine of 30 plus sine of 60, because what we would need to do is use our formula up above in the box. So this one's going to be false. And likewise, cosine of pi plus pi over 2 cannot be cosine of pi plus cosine of pi over 2, because that's not using the formula from the box up above. So once again, cosine does not distribute. And the same thing for tangent. So the tangent of 15 minus 10 can't be the tangent of 15 minus the tangent of 10. Because just like sine and cosine, tangent does not distribute. So the point of these three questions is trig functions do not distribute. Okay, so that might take some getting used to, but the main thing to remember is that we have special formulas that help us to figure out sums and differences. Okay, so it's just not as easy as take the sine, cosine, or tangent and distribute it across the parentheses. Okay, so once again, why do we need formulas like this? Well, I kind of explained something before. You know, we have values of stuff on the unit circle, but there's plenty of other angles that are not on the unit circle, and you might ask, well, how can we find those values without a calculator? And so this is one of the ways we can do that. So taking combinations of stuff that we do know, we can find stuff that we don't know. And in addition, we can prove some additional identities, and then later in the chapter, not in this section, we'll be solving trig equations. So let's jump in and do some examples. So our first example, we're going to find the exact value of the following expressions. So our first one is the cosine of 75 degrees. So our job here is to figure out how can we either add or subtract two angles to get 75 degrees. So we want to think about our unit circle values. So in degrees, it would be 0, 30, 45, 60, and 90. Those are our basic unit circle angles in the first quadrant. So, will any of those give us 75? So the ones I'm looking at are 30 and 45. So what I can do is I can write cosine of 75 is equal to cosine of 30 degrees plus 45 degrees. So notice I didn't write cosine of 30 plus cosine of 45. I simply split the 75 up into 30 plus 45, but I still have a single cosine. Okay, so now that we've done this, now we can apply our cosine of a sum formula. So we're going to use formula 3. So I'm just going to make a note of that over here. So when you go back and reference, it'll make sense. And so formula 3 tells us to do cosine of 30 times cosine of 45 minus sine of 45, or sorry, sine of 30. It really doesn't matter. We can multiply things in any order, but just to keep it the same, times sine of 45. Okay, so this is our whole cosine formula. Cosine of 30 times cosine of 45 minus sine of 30 times sine of 45. So now what we need to do is actually sub in values for each of these trig functions. So the cosine of 30, if you remember from the unit circle, is the square root of 3 over 2. And the cosine of 45 is the square root of 2 over 2. And then the sine of 30 is 1/2. And the sine of 45 is, again, square root of 2 over 2. All right, so now that we've substituted in every single one of these trig functions, we can go ahead and simplify. So when we simplify this, we're going to basically multiply the first two fractions, multiply the second two fractions, and then we're going to subtract. So to multiply the first two fractions, I'm going to multiply across the top. And so I get the square root of 6 over 4. So just a reminder, when you're multiplying square roots, you could multiply the two numbers that are underneath them. Adding is a little different, but multiplying isn't too picky. And then for the second two fractions, we're going to have 1 times the square root of 2, which is the square root of 2, over 2 times 2, which is 4. So finally, I can add these two fractions together, and we already have a common denominator of 4. So all I have to do is add the two things on top and put it over 4. So one thing to remember with square roots is that when you're adding square roots, you can only add square roots that have the same number underneath it. So 6 and 2 are different, so we can't add them together. The best we can do is just write it as a difference. Okay, so this is our final answer for the first example. In this second example, we have the sine of pi over 12. So once again, I want to try and think of two values on the unit circle that will add or subtract to give me pi over 12. So these can be a little bit trickier, so let's remind ourselves of what our angles are in radians on the unit circle. So our most basic ones, we have 0, pi over 6, pi over 4, pi over 3, and pi over 2. So the two I'm looking at are going to be pi over 4 and pi over 3. And the reason for this is when I add something with a denominator of 4 to something with a denominator of 3, my first thought is, well, their least common denominator is going to be 12. And so that's a good sign that that's probably the pair of angles that I want. So let's check to make sure. So pi over 3 is bigger, so we probably want to do pi over 3 minus pi over 4 to get pi over 12. So let's check and see what that gives us. So we have pi over 3 minus pi over 4. So if we convert these to fractions with denominators of 12, to go from a denominator of 3 to a denominator of 12, we had to multiply by 4. So we have to do the same thing on the top. So this first fraction is going to become 4 pi over 12. And in the second fraction, we had to multiply 4 by 3 to make it 12. So the top is going to become 3 pi. And so 4 pi minus 3 pi indeed gives us pi over 12. So that's good. So this is the pair of angles I'm going to use. Okay, so we can rewrite sine of pi over 12 as sine of pi over 3 minus pi over 4. All right, and then I can apply my formula. So this time we're going to use formula 2 because that's a sign of a difference. So if we expand this using formula 2, we'll get sine of pi over 3 times cosine of pi over 4 minus cosine of pi over 3 times sine of pi over 4. Okay, and then we can sub in values. So the sine of pi over 3 is the square root of 3 over 2. The cosine of pi over 4 is the square root of 2 over 2. The cosine of pi over 3 is 1/2. And the sine of pi over 4 is, again, square root of 2 over 2. So now we can multiply our pairs of fractions. So we get the square root of 6 over 4 minus square root of 2 over 4. And this again simplifies to square root of 6 minus square root of 2 all over 4. So you'll notice that we ended up getting the same answer as part A. And that's fine, even though these two angles were different. So this might happen sometimes, but not all the time. So don't just assume that everything you do in this section is going to give you root 6 minus root 2 over 4. That won't happen. But hopefully this gives you an idea of how to expand using the sum and difference formulas. So we're going to try one more using the tangent formula. So this one we have tangent of 165. So this one might be slightly more difficult just because now we're dealing with an angle that's not in quadrant 1. So let's maybe think about what are our angles in quadrant 2. So we know in quadrant 1 we have 0, 30, 45, 60, and 90. And then quadrant 2 we haven't talked about quite as much. So maybe let's talk about those angles. So after 90, let me think, we would have 120, 135, 165, and no, not 165, 150, and 180. Okay, so this is quadrant 1, this is quadrant 2. So I want to ask myself, what two angles out of this list will add together to give me 165? So what I'm looking at is 135 and 30. So I think you would agree that if we take 135 and add 30 to it, we'll get 165. So I'm going to rewrite my tangent expression as tangent of 30 degrees plus 135 degrees. Okay, so if we expand this out using the tangent formula, we would get tangent of 30 plus tangent of 135 divided by 1 minus tangent of 30 times tangent of 135. Okay, so let's plug in our values for tangent. So the tangent of 30 is 1 divided by the square root of 3. The tangent of 135 is negative 1, so we're going to put a minus 1. And then on the bottom, we get 1 minus 1 over the square root of 3 times negative 1. So if I continue to simplify this, I need to get a common denominator on the top. So we'll have 1 over the square root of 3 minus the square root of 3 over 3. And on the bottom, we'll have 1 plus 1 over the square root of 3. So again, we can add our fractions on the top to get 1 minus the square root of 3 over the square root of 3. And on the bottom fraction, we'll get square root of 3 plus 1 over the square root of 3. So now if I divide these two fractions, I just get 1 minus the square root of 3 over the square root of 3 times the square root of 3 over the square root of 3 plus 1. So finally, these two square root of 3's cancel, and my final answer is 1 minus the square root of 3 over the square root of 3 plus 1. Okay, so it's worth noting here that I did show you how to do this with the tangent formula just because I wanted you to see how it's used. But another way we could have done this, so I'll make a note of this in red, another way that you could have solved this problem is find sine of 165, find cosine of 165, and divide. So remember I told you when we first went over the formulas, we could have used that sine over cosine idea, which we could have done that precisely here. And for some of you that might be easier just because if you're remembering sine and cosine values on the unit circle, you may not remember the tangent values. You might have to solve for those every time. So sometimes finding the sine and cosine first is a little easier because you don't have to solve for tangent every time. Okay, so you can try that and see if you get the same answer. They should come out the same. They might just be a little different through some algebra. Okay, so hopefully that makes a little bit of sense. So let's try another example. So far in this section, we've been taking something that's smaller and we've been expanding it. But sometimes we can use these formulas in the opposite way as well. So let's look at the following example where we have sine of 42 times cosine of 12 minus cosine of 42 times sine of 12. So this is like the expanded form of one of the formulas. So we have sine times cosine minus cosine times sine. So that tells me that this is actually just formula 2. It's a difference of sine, or sine of a difference. So formula 2 tells me that this is actually just sine of 42 degrees minus 12 degrees, which if I simplify those parentheses, that's just sine of 30, which we know from the unit circle is 1/2. So this just goes to show you that sometimes we might be given some angles that we don't know, and maybe instead of expanding it out using angles we don't know, maybe we have to condense it down to get to an angle that we know. So that's just one example of something you might see. So now let's try something else. So in this next example, we're going to express sine of 3x in terms of sine x and cosine x. So this one's going to be a little more algebraic. We're not going to get a numerical answer here. So let's start by writing sine of 3x. And I want to think about how can I split up that 3x into a sum. So my first thought is, well, maybe I could just do x plus 2x. Why not? All right. So what I can do, now that I've written 3x as a sum, is I can expand it using my sine of a sum formula. So that's formula 1, and what's going to happen is we'll get sine of x cosine of 2x plus cosine of x times sine of 2x. Okay, now I notice that I still have a cosine of 2x and a sine of 2x. And I want my answer with just sine of x and cosine of x. So I still need to take these cosine of 2x and sine of 2x, and I need to expand them out more. Okay, so in this next step, what we're going to do is rewrite those two things as another cosine of a sum and another sine of a sum. So we'll have sine of x and cosine of 2x. There's only one way to add two things to get 2x. We just have x plus x. And then we'll have cosine of x, and then we'll do the same thing with sine of 2x. So we'll have sine of x plus x. Okay, so now what I can do is within each of those terms, I can expand the cosine of x plus x and the sine of x plus x. So the cosine of a sum will be formula 3, and the sine of a sum will be formula 1, just so you have a reference. So this will turn into sine of x, and then we're going to open a parentheses, and cosine of x plus x is going to be cosine of x minus sine of x, and then we'll have our plus cosine x, and then sine of x plus x, I'm going to open another parentheses, will be sine of x, cosine of x, plus cosine x, sine x. So I kind of ran out of room there, but this is just multiplied with that cosine of x right here. Okay. Okay, well, let me rewrite that now. So cosine of x. Okay. So we can simplify this a little more now. So you'll notice that inside this first set of parentheses, we have two identical factors of cosine and two identical factors of sine. So we can simplify that to cosine squared of x minus sine squared of x. And in the second parentheses, I have two identical terms of sine x times cosine x. So this will just turn into 2 times sine x times cosine x. Okay, and then finally I can distribute across these parentheses. So here, if I do sine of x times cosine squared, I'll get sine x cosine squared x minus sine cubed of x. So when I distribute sine to sine squared, I get sine cubed. And then the second term, I'm not really going to distribute, but I have two factors of cosine, so I can rewrite this as 2 times sine of x times cosine cubed of x. Cosine squared, my bad. Okay, So now you might notice that we have two terms that both have a sine x times cosine squared x. So we have this term and we have this term, so we can add them together. And so our final answer is going to be 3 times sine of x times cosine squared of x minus sine cubed of x. So now I've taken sine of 3x and I've written it completely in terms of just sine x and cosine x. All right, so now that we've talked about how to use the formulas, we've done a little bit of algebra with them. Now we're going to go back to what we did in the previous section and try to prove some identities. So just to remind you, when we prove an identity, we're not solving an equation, and we're also not simplifying both sides of the equation and seeing if we get the same thing. So what we want to do is we want to pick the complicated side and try to simplify it and turn it into the other side. So in this first example, we have sine of x plus y over cosine of x times cosine of y is equal to tangent of x plus tangent of y. So the first thing I'm going to do is pick the more complicated side to start with. So I'm going to go with the left side because to me that looks a lot more complicated. So we're going to start with sine of x plus y over cosine of x cosine of y. And just one more thing about identities. So I believe I told you in the previous section that your homework problems about identities, they're not my favorite. So instead of having you write a proof, they'll have the proof written for you, and then you have to fill in some blanks. My advice when you're trying to prove these is, yes, do your homework, but also see if you can prove them yourself without the aid of the proof that's given to you on WebAssign. I think that will make it better come test time, because for the test, I'm not going to give you the proof. You're going to have to prove it yourself. Now, it won't be a super complicated one, and I think I also said I'll post some example problems for you to try yourself so you can get the idea of the difficulty I'd be looking for on a test. Okay, so back to this example. So we started with the left side, and now I want to use algebra to simplify it down. So the first thing I might do is I notice on top I've got that sine of a sum formula, which I can expand out. So I'm going to write sine of x cosine of y plus cosine of x times sine of y divided by cosine of x times cosine of y. Okay, so now that that top is expanded out, I notice that my denominator has a single term. So it has two things multiplied together, but the important thing is that they're not added together. So if we have a single multiplied term on the bottom with no addition signs, what we can do is we can split up that sum on the top and place each term with a denominator of cosine x, cosine y. So let me write down what I mean. So we can split this up into sine x cosine of y over cosine of x cosine of y plus cosine of x sine of y over cosine of x cosine of y. So notice what I've done. I've split up the numerator and I've put the denominator with each fraction that I split up. Okay, and notice if you were to go backwards and re-add this to get the previous step, that's what you would get. So we don't add our denominators, we only add our numerators. So that's why this makes sense. Okay, so how can I continue to simplify this? Well, you might notice that in the first fraction, we have a factor of cosine y on the top and a factor of cosine y on the bottom. And likewise in the second factor, the second fraction, I have a factor of cosine x on the top and a factor of cosine x on the bottom. So what I'm left with is sine x over cosine x plus sine y over cosine y. And now if I remember that tangent is just sine divided by cosine, I get that this is equal to tangent of x plus tangent of y. So this is good. We got the right side of the equation. Okay, so let's try a couple more like this. So our next example, we have cosine of x plus pi over 3 plus sine of x minus pi over 6 is equal to 0. So I think the more complicated side of this one is the left side. So let's go ahead and start with that. So we have cosine of x plus pi over 3 plus sine of x minus pi over 6. And I want to see if I can simplify that down to get 0. So the first thing I'm going to do is just apply formulas to each of these trig functions. So notice we have the cosine of a sum, the sine of a difference. So I'm just going to expand each of those out using their respective formulas. So what we get is we get cosine of x times cosine of pi over 3 minus sine of x times sine of pi over 3. So these two terms come from the cosine, and then we're going to have two more terms for sine. So we have sine x times cosine of pi over 6 minus cosine x times sine of pi over 6. Okay, so just to reiterate, let me see if the highlighter will work this time. And, oh, there we go. All right, so this cosine right here turns into these two terms. So that's our entire cosine formula. And then, let me change colors. This sine formula here turns into these two terms here. So we've expanded out every single thing in this identity. Okay, so let's go back to the pen. Okay, so now I want to see how much I can simplify this. So we know some of these numbers, like cosine of pi over 3, we know is just the square root of 3 over 2, so we can sub that in. And then we know the sine of pi over 3 is, or sorry, cosine of pi over 3, I'm getting them mixed up, is 1/2, and the sine of pi over 3 is square root of 3 over 2. Okay, and then the cosine of pi over 6 is the square root of 3 over 2, and the sine of pi over 6 is 1/2. So I'm going to sub that in as well. Okay, so now what I notice is that over here I have positive cosine x times 1/2, and over here I have negative cosine x times 1/2. So these two terms are going to cancel out. They're going to add each other out. Likewise, the next two terms we have left, we have negative sine x times root 3 over 2, and we have positive sine x times root 3 over 2, which are again going to add each other out, and so we're just left with 0. And so that was the right side of our identity, and so that's what we wanted to show. All right, our next example, we have cosine of x plus y times cosine of x minus y is equal to cosine squared of x minus sine squared of y. So I think the more complicated side is again the left side, so let's go ahead and start with that. So we have cosine of x plus y times cosine of x minus y. So the first thing I'm going to do is expand each of these formulas out. So I'm going to open up parentheses, and I'm going to get cosine of x, cosine of y, minus sine of x, sine of y. And then I have another set of parentheses for the second cosine. So we have cosine of x, cosine of y, plus sine of x, sine of y. Okay, and then from here, you might notice that these two factors, or these two sets of parentheses, look exactly the same, except for one has a minus and one has a plus. So if you remember those factoring problems that we did in the previous section, you might recall that this is just a difference of squares. So if we were to FOIL this out, what we would get is cosine squared x times cosine squared y minus sine squared x times sine squared y. Okay, so that's multiplying these two factors together. But I still want to get to cosine squared x minus sine squared y. So I have part of that showing up, but I still need to get rid of that cosine squared y and that sine squared x. So this is where this starts to get a little tricky. So what I'm going to do is I'm going to take each of these things that I want to get rid of and figure out how can I write it in terms of the things that I want. Okay, so if we think about our Pythagorean identities, so let's go off to the side. We remember that we have, and I'm going to be careful not to use x or y, I'm going to use theta because we're going to use it twice. So we have sine squared of theta plus cosine squared theta is equal to 1. So maybe you notice for cosine squared of y, we can rewrite that as 1 minus sine squared of y. And sine squared of x, I can rewrite as 1 minus cosine squared of x. And so the reason I'm choosing to do this is that now the thing that I want, I just want to have cosine of x and I want to have sine of y. So what I've done now is I've taken the cosine squared of y and gotten it in terms of sine squared of y, and I've taken the sine squared of x and gotten it in terms of cosine squared of x. So this is important because now the only things left in my equation are the things that I want. I just need to simplify them down a bit more. Okay, so when you get stuck in one of these proofs, because sometimes they can be pretty tricky, look at where you want to go and figure out, like, is there a way I can get rid of the stuff I don't want by making it look like the things that I do want? Okay, if that makes sense. So let's try and simplify this. So we can distribute the cosine squared of x across this parentheses. So we get cosine squared of x minus cosine squared of x sine squared of y. And then I can distribute the negative and the sine squared of y across this parentheses. So I get minus sine squared of y plus cosine squared x sine squared y. And let me just get that out of the way. Okay, so now my final step is I notice I have a negative cosine squared x sine squared y, as well as a positive cosine squared x sine squared y. So those are going to add away, and I'm left with cosine squared of x minus sine squared of y. And so I've reached the other side of my identity, and that's what I wanted to do. Okay, we're going to do one more example of an identity, but it's sort of disguised. So in this example, we're going to actually prove that the period of tangent is pi. So what this means is we want to prove the following identity. We want to prove that tangent of x plus pi is equal to tangent of x. Okay, so this makes sense for the definition of the period, because remember, a period was basically the distance before one of these graphs starts repeating itself. So if we're saying add pi to an angle and we get that same angle back, that's exactly what we want it to happen, right? We want it to repeat after a distance of pi. So this identity makes sense, and that's what we're going to prove. So the more complicated side of this identity is probably the tangent of x plus pi on the left. So that's what I'm going to start with. So I'm going to say tangent of x plus pi is equal to tangent of x plus tangent of pi divided by 1 minus tangent of x times tangent of pi. Okay, now the tangent of pi, remember the sine of pi is -1, and, sorry, I have that backwards. So if we're thinking sine over cosine for the tangent of pi, the sine of pi is equal to 0, and the cosine is -1. So tangent of pi is just going to simplify to 0. So my formula turns into tangent of x plus 0 over 1 minus tangent of x times 0. So simplifying a little bit more, this is just tangent of x over 1, which gives me tangent of x. And that's good. That's what I wanted, because that was the right side of my equation. Okay, so we're done with identities for this section, but we're going to try a few more slightly complicated problems, just in case they come up on your homework or a test review or a test. So in this next example, we're going to find the exact value, but this one's going to be a little tricky. So we have the tangent of sine inverse of 3/4 minus cosine inverse of 1/3. So this problem, I get that it looks really complicated, but the idea here is for you to notice that it's just a tangent of a difference, okay? What's in here might look complicated, but really they're just playing the roles of our normal angles, U and V, all right? It's no different, it just looks more complicated. So the first thing I'm going to do is actually expand this out using the tangent of a difference formula. So what that'll give me is I'll have tangent of sine inverse of 3/4 minus tangent of cosine inverse of 1/3 divided by 1 plus tangent of sine inverse of 3/4 times tangent of cosine inverse of 1/3. Okay, so now that I've expanded this out, I noticed that what this boils down to is a bunch of those problems like we saw in section 6.3. So remember in 6.3, we did those problems where we had like a composition of a trig function and a inverse trig function. Well, this is exactly what we have here. So the way that we solved those is we drew some triangles and we used that to help us solve the expression. So because I have two different expressions here, I'm going to need two different triangles. So my first triangle, I'm going to get from that first expression of tangent of sine inverse of 3/4. So I'm just going to call this angle theta 1. So if we have sine inverse of 3/4, that means my sine is equal to 3/4. So that means my opposite side is 3 and my hypotenuse is 4. So that also means, through Pythagorean theorem, that my adjacent side is equal to the square root of 7. So that's my first triangle. And then my second triangle, I'm going to do the same thing, except I'm going to use that 1/3 to give me my information. So we're going to call this one theta 2. And let's see what we can get from this. So if cosine inverse is 1/3, that means cosine is equal to 1/3. So that means the adjacent side is 1 and the hypotenuse is 3. And then from Pythagorean theorem, we get that the opposite side is 2 times the square root of 2. Okay, so let's see what we can do with this. So maybe I'll highlight the different parts so you can see which triangle we're using for which piece. So this expression here, oh, come on, highlight. All right, good. So this expression here and this expression here, we're going to use this triangle right here. And then this expression here, come on. Oh, come on, highlighter. Okay, well, we're not going to highlight that one, but the last two expressions are going to come from the second triangle. Okay, so let's substitute those values. So if we go to our first triangle, the tangent from that first triangle is going to be 3 over the square root of 7, because we need the opposite side over the adjacent side. So in place of these highlighted expressions, I'm just going to write 3 divided by the square root of 7. And then these ones that I didn't end up highlighting, we're going to use the second triangle. So the tangent from that second triangle is 2 times the square root of 2. So in place of each of those, I'm just going to write 2 times the square root of 2. And then I need to simplify this complicated fraction. So on the top, we can get a common denominator, which would be square root of 7. So we have 3 over the square root of 7 minus 2 times the square root of 14 over the square root of 7. So we got that square root of 14 because we had to multiply square root of 7 on the top. And then on the bottom, we're going to have 1 plus 6 times the square root of 2 over the square root of 7. Okay, so the top two fractions I can go ahead and add together because they have the same denominator. So I can say that this is 3 minus 2 times the square root of 14 over the square root of 7, and then that's all divided by the square root of 7 plus 6 times the square root of 2 over the square root of 7. Okay, so now that I have a fraction divided by a fraction, I can flip that bottom fraction and multiply it. So we have 3 minus 2 times the square root of 14 over the square root of 7 times the square root of 7 over the square root of 7 plus 6 square root of 2. So now these two square root of 7s are going to cancel, and our final answer is 3 minus 2 square root of 14 over square root of 7 plus 6 square root of 2. Okay, so that is our exact answer. Okay, so let's just reiterate what we did. So we started with this very complicated looking expression, but we said that it's just the tangent of a difference. So we can expand it using one of our sum and difference formulas. And then for each of these composite expressions that we get, we can draw a triangle and figure out what it is. So this was from 6.3. And then when we do our algebra very carefully and simplify it all the way down, that's how we get to our answer. Okay, we've got one more example. Hopefully you're not too tired yet, but we're just going to do one more example. So we're going to evaluate each expression under the given conditions, and we're going to keep the answer exact. So this one's going to be similar to the one we just did. So we have the cosine of theta minus phi. So this letter right here is another Greek letter called phi. Some of you might call it phi. That's another way to say it, like the sorority. Okay, so we're going to start with cosine of theta minus phi. And so what we want to do with this is we want to expand it, just like we did in the previous example. So if we look at our cosine of a difference formula, this will turn into cosine of theta, cosine of phi, plus sine of theta, sine of phi. Okay, now the question is, how do we figure out what these trig functions are actually equal to? Well, that's where this extra information here comes in. So once again, we're going to have to figure out, well, how do we get the triangles to figure out what the other trig functions are for this? So for theta, so what I'm going to do is I'm going to draw two triangles at the bottom. Okay, so this first triangle is going to be for the angle theta, and it says that theta is in quadrant 4. So my triangle is going to look like this. And the angle is going to be theta. So we have that the cosine of theta is 3 over 5. So cosine is adjacent over hypotenuse, so that tells me my hypotenuse is 5, and the adjacent is 3. So if we use Pythagorean theorem, we would get that the missing side is 4, but since it's in quadrant 4, we need to make sure that we write it as negative 4. So notice how that side points downward, so that tells us that it's going to be negative. All right, so we've got our triangle for theta. Now we need to get our triangle for phi. So for phi, we're given that phi is in quadrant 2. So I'm going to draw my triangle in quadrant 2 and label that angle phi. And then we're told that the tangent is equal to negative root 3. So tangent is opposite over adjacent. So you can think of negative root 3 as negative root 3 over 1. So I know that my opposite side is going to be root 3, and my adjacent side is going to be 1. Now I need to decide where to put the negative. Well, if you look at the drawing of the triangle, the negative has to go with that x side, right? So it has to go with the 1 because that's the side that's pointing to the negatives. The root 3 side is pointing up, so that one can't be negative. So if we use Pythagorean theorem to get the hypotenuse, we should get 2 for our hypotenuse. And so now we've solved this triangle as well. So the whole point of getting these triangles is now we can get any trig function that we want for these two angles. So now I can actually plug in values in the formula that I have written at the top. So for cosine of theta, I'm going to look at the first triangle, and I know that cosine is adjacent over hypotenuse, so that's just going to be 3 over 5. Okay, cosine of phi, I'm going to look at the second triangle, and I'm going to do adjacent over hypotenuse, which is negative 1 over 2. Now I'm going to go back to the first triangle, and I'm going to find the sine. So the sine of theta is going to be opposite over hypotenuse, which is negative 4 over 5. And then finally, sine of phi, I'm going to go back to the second triangle and find the sine. So the sine is again opposite over hypotenuse, so we have root 3 over 2. And now that I've subbed in a number for each of these functions, I can go ahead and simplify. So 3 over 5 times negative 1/2, I'm going to multiply across the top and the bottom and get negative 3 over 10. And for the second two fractions, again, I'm going to multiply across the top and get 4 square roots of 3. And on the bottom, 5 times 2 is again 10. So my last step, I have two fractions added together. They already have a common denominator, so I'm just going to add across the top and get negative 3 minus 4 square roots of 3 over 10. So this is my final answer. All right, so hopefully all of that wasn't too confusing. I think we used the formulas enough to where you should have the idea. But again, if you have any questions, let me know. And this concludes our 7.2 lesson.